All right, so thanks for letting me speak. I'm going to be something totally different. The science for me is going to be glossed over in that the instruments produce data, and we're going to talk more about the engineering aspect of it. It's already been really fun this morning to hear a lot of engineering-oriented talks and things that have been tried and work and don't work. So some of this is going to be not new information because you're already going to be familiar with the challenges, but hopefully it's a good starting point. And when I ask conveners what I want to talk, I said, well, I kind of got three things I think might be interesting. And the response was, they all sound great. And so I'm going to take three long talks and smush them into one here. The first one is I want to talk about why I think tilt meters are often undervalued. Don't see a lot of tilt data, though it is changing. I'm partial to that. That's what helped us start the company a decade ago. But they have a lot to offer, I think. There's also been a lot of talk about getting data back, telemetry, especially if it's an instrument you don't know if you're ever going to see it again. That's becoming really important. We've got some lessons that we've learned and some experimental telemetry things that we've tried that I wanted to share. And then lastly, some tips on working with instrument makers, which is probably the part that you're all going to be pretty familiar with already. But I do want to start out by saying, of course, I don't collect data, I make instruments. So every piece of data that's shown comes from somebody. I know several of these people are on the Zoom. Some aren't, they're customers. Some of the data is from our stuff, some of it's from competitors. Just thanks to everybody for letting me share their work. Okay, so talk one. Tilt meters, they can be used for pretty much anything that involves deformation, and that's what we're interested in as geoscientists mostly, is when things are changing. So there's a lot of applications, of course, in construction. We've got one that's being used to flip a bridge segment over in the Netherlands this summer, which is going to be kind of cool. Different application than usual. Mining, tunneling operations, of course, use them. Volcanology, geothermal. But in glaciological applications, they're particularly valuable because you're dealing with really large deformations compared to a lot of these other things. In geothermal work, for example, we're doing a deployment very soon of a downhole tilt meter where we're expecting tilts on the range of something like 10 nanoradians a year. So very, very, very small and very hard to detect. A lot of these glaciological applications, we can get away with less expensive sensors, collecting at a higher rate because your deformations are a little easier to see generally, not always. There's been some talk this morning about GPS stations, a little bit about seismic. To me, tilt kind of fills a nice gap in between those. GPS, we're generally looking at these very long-term trends in movement and deformation. Seismic, we're looking at, I say high frequency in quotes, dealing with electronics, calling seismic high frequency is semi-comical. But okay, a hertz, tens of hertz maybe. Tilt fills that nice. I'm interested in what's happening on a days to weeks time scale. The other advantage is it's also really inexpensive. And there may be some argument on some of these numbers. I know at lunch we were talking about GPS stations that had another digit in a price after they were deployed. But so run-of-the-mill seismic station, mind you, these are roughly terrestrial prices for more traditional deployments than you're doing. 20 to 40K. GPS, let's call it 10 to 30. Tilt, you can get down to roughly a kilobuck, a little bit less, depending on exactly how you want to do powering things, or up to $15,000 or $20,000 for the really complicated borehole instrumentation. But I'm not going to say that tilt is all amazing. It certainly has its problems, like every instrumentation method that you might use. Long-term stability of tilt is known for being not so great. That's where things like GPS can come in really nice as a complement to it. There's a lot of shallow signal sources if you're putting your tilt meters on the surface or just under the surface. Things like clay layers drive us nuts in a lot of on-land deployments. Even being close to a lot of trees and having a lot of wind, we can see tilt signals from that. Thermal expansion of topography as the sun goes over it causes tilt signals, all kinds of weird shallow signals. I'm gonna actually skip calibration, we'll come back to that. Coupling, how you're going to couple that tilt meter to the thing that you want to measure. If it's rock, that's relatively straightforward. If it's loose snow, it's a little bit less straightforward how you need to couple that and how you can ensure that you don't have any bizarre effects from having done that. Comes to mind of having some Pelican boxes with tilt meters in them that were buried that ended up floating out of the ground and causing all kinds of weird signals over a long-term study. Then temperature, there's a lot of, depending on the technology you're using to measure tilt, there can be pretty strong temperature dependence of the instrument. And we're going to talk a lot about temperature later on. But calibration, so to come back to that, when we're getting down into these very high resolution tilt instruments now, sub-microradian, even into nanoradian, it's incredibly hard to produce a known tilt of something like 5 nanoradians. So actually measuring it and getting resolution that we think is nanoradian or sub-nanoradian is quite possible. Knowing exactly what that tilt value is getting to be pretty tricky. And we've done a lot of work, Scott DeWolf, Clemson has done a lot of work on trying to figure out good calibrating methods. And it's an ongoing effort. Not Juno, but I want to quickly show a couple of applications of tilt meters. So here we're on the weights, everybody, background slide. Grounding lines rapidly retreating, flow speeding up something like 20% over the last 5 years. So what's going on to cause this? One of the ideas that's been out there is that this tidal flexure mechanism can pump warm brackish water up under weights and cause what we're seeing. As a paper from Brian Walker back in 2013 showing you've got your ice shelf, tide going up and down, and you get this beautiful, in theory, engineering textbook solid beam bending problem with a pinning point, right? And we can see how maybe this going up and down could produce a pump. I was talking with Sam at lunch. Actually, part of my PhD work got a hold of some Willens ice core, or sorry, tilt core, and did real-time tidal simulations on it to look at permeability changes. It's pretty interesting stuff there, but again, we're gonna cruise past the science. Kaya, who's on the call, hi Kaya, thanks for letting me use your data. Deployed a line of tilt meters, various types, across the grounding zone and produces really interesting plot. So the gray line is modeled tide, and then the colored lines are the tilt signals that she retrieved. So out on the floating ice, bottom of the plot here, we see really pretty nice agreement between the tilt and the tidal signal that was predicted. As we go more towards grounded ice, that signal fades out some. And then an interesting thing happens once we pass the grounding line. It's anti-phase, anti-correlated. So if we look at a plot of surface elevation along weights and the correlation coefficient between the predicted tide and the tilt, we see that after on floating ice, we have strong correlation. Right when we hit the grounding line, we go to anti-correlation because we're pivoting about that point, so the sense of tilt's changing. Science works, the instruments work. More interesting to this crowd probably was some student deployments of tilt instruments at Von Loos Icefall that Kaya was also involved with. Just to say, when you're talking about rapid elevation changes and things like breaking of ice, that sounds like tilt meters to me. So skip over that in effort not to make this 3 talks length. Yeah, so these are the tilt meters that they deployed, these little MEMS inclinometers or tilt meters. This particular one is just a little bit larger than a hockey puck. And I brought a huge case of instrumentation with me to play with later this week when we've got some time. But they went out and deployed these and collected data for a little longer than a week here. And saw some pretty significant tilts. You know, we're seeing plus or minus 40 thousandths of a degree tilts here. And that's what I mean by irriglacial signals are huge. So that's a great signal. They were able to see that they believe there's some subglacial hydrology driving this process as they saw some daily flow speed and temperature variations along with the tilt. And again, Kai, I'm probably not getting nearly as deep into this as you would like, but that's about all the time I've got to say. So why don't we use tilt more? I think it's probably suffering a lot of the same biases as gravity and magnetics. When you get seismology, you go, oh, this is great. We don't need any of that non-unique potential fields methodology anymore. We all know that seismology and radar definitely don't make any assumptions about their data, right? And it's all very, very definite. But I think that's one of the reasons that tilt sort of hasn't been super popular. All right, moving on to talk two related. Now you've got your instrument out there, your tilt meter, your drone if you can still do that, and you need to get that data back. There's a lot of ways that you can do that now. LoRa and LoRaWAN are becoming pretty well-known methods if you've got low rate data. Something like a tilt meter that's got data once an hour. You can send it back over these very low bandwidth, very low power connections to a central gateway or concentrator, and then pipe that out somehow from there. And it's really pretty inexpensive to do. Those LoRa radios, sub $100, and you can get many kilometers of range. But again, you're very limited on the airtime. I believe the duty cycle limit is a couple percent. So you're not getting large amounts of data out. There's always Iridium. We'll have a slide on that in a second. Starlink is becoming a very interesting way to get your data out of the field. You can use traditional Wi-Fi, 2.11, whatever you like, to communicate between instruments, or even back to the internet if you have a way to get out, or traditional VHF backhauls. They've worked for decades. They're going to work for decades more. Iridium small data burst, SDB technology, relatively inexpensive to do. I say relatively because you're looking at a dime to 50 cents per packet. And the packets you're getting, at least from the provider we use, which is ground control, are about 50 bytes, not megabytes, bytes. So you can't pack a lot of data in that. And there's a monthly line fee that's on the order of $12. So not the cheapest way, but if it's low rate data like tilt, you can do this. Modems are a couple $100 and they don't have much wind loading, so you can stick them on a very small pole and they last quite a while. Starlink is sort of changing the game though. It's got a few big challenges that we've seen. Deploying out a couple of projects. First is power consumption. Starlink Mini can pull up to 40 watts of power continuously. That's a lot for these field systems that you want to leave out. It can pull as little as 15 to 20 in idle though. If you have an older model that has the heating element it's way high compared to that. The mechanical robustness of the antenna leaves something to be desired if you're going to leave it out for a very long period of time in the harsh environments that we deal with. If you're putting it on the roof of your house, probably not that bad. But we have seen wind-driven stones in through the antennas. They're not that strong. And they don't provide a publicly routable IP. You don't get a static IP address that you can open up ports on and get into your equipment. So we encountered all of these recently on this low power distributed temperature sensing system down in Antarctica. So I think several people have heard we were talking about again at lunch, the almost very successful hot water drilling project. Made it a long ways though. And we got a fiber down over 900 meters. So the idea was we want to leave this running remote for roughly 2 years. And there's not going to be any opportunities for site visits. So it needs to be very reliable and can't have something pulling 20 to 40 watts of power continuously. It's just not going to work, even with the big box of batteries. So we tackled this a few ways. You can see the Starlink up there on the very top of this tower. I'm going to talk a little bit about how that particular one is mounted and some other options. Then we had a computer and power management system, and the fiber interrogator is down here. eventually should end up on this bracket. Didn't for some fun logistical reasons. So to manage the power, we actually created this thing. We call it the field sequencer. We created it for this project, but I think it's going to be really useful for other projects. We've already used it in a couple. That has a sleep power. It's very low. It's under a milliamp of sleep power, 12 volts. And you can schedule events by day of week, time of day, and it can control up to 4 external relays. So you can have, for example, on that deployment, we had the Starlink, we had the distributed temperature interrogator, and we had the industrial PC on one of these. And we were able to sequence all of those on and off and save an absolute ton of power. You can override via serial each of the commands and your schedule. So for example, we would schedule Starlink to come on and stay on for 30 minutes. But if the system collected the data more quickly and the industrial PC said, okay, I'm done, it could go ahead and turn that off earlier and save us even more power. It has state of health monitoring built in, like your battery bank voltage, how much current everything's pulling. And it has a lot of connections for external sensors. The firmware is open source, so you can play with it, make it do pretty much whatever you want. So that's how we manage power. We just turned on once per day with the Starlink. A word on Starlink power cables. Has anybody used the Starlink stock power cables? Yeah, they're awful. So they send you I think they need a cable with the kit. And the power supply they send you, if you notice, is pushing 40 volts. I don't remember exactly what they said. They are really tiny conductors in that cable. So if you go to the field and you plan on chopping the end of that cable off and hooking into your 12-volt field battery bank, it's not going to work. In fact, with the Mini, we measured it. You get a voltage drop, you get 9.4 volts at the end of the cable. And the Starlink will either not work, or it will do this very fun kind of working boot loop, where you think you've got connection and then it drops and just does not do at all what you expect. So you either need to step it up to have a 12 to 24 volt, 36, and 48 volt converter if you're going to use that power cable. Or what we do a lot of the time is get the power cable, cut it about 6 inches long, and put it on a 12 gauge wire running down to our power source. Then you get very minimal voltage drop. Also, I like using things like SJ0OW cord or something that's going to be a little bit more weather resistant than the stock Starlink cable. Mechanically, so we've tried a few different things. We've built this bracket out of some welded square tube and plate to put it on poles. It works fine. It still frustrates me some that they have this really nice piece of phased array antenna technology and they insist on mounting it with a 60,000th inch thick piece of injection molded PA6 plastic. So you can rip that off in high winds relatively easily. The best thing we found to do is mount it in a Falcon box or whatever your favorite brand of box is. It's RF transparent, it protects it. The downside is this is a lot more wind loading if you're putting it on top of a pole or a tower. So sometimes the bracket may still be the way to go. But we haven't had one in a box like this fail yet. I'm sure there will be some fantastic failure mode, but we at least haven't had them break apart. Getting into the devices remotely is not a huge problem, but I thought it might be worth mentioning. Since you don't have that publicly routable IP, you can either set up a little Amazon Nano server somewhere or have a server here that your remote devices connect to and then use a reverse tunnel to go back into it. Or even easier, just using a VPN service. There's a company called Tailscale that we use. It's $6 a month for 50 devices. And it lets you get around this problem totally. And they have, the key thing is they have non-expiring certificates that you can install on machines. Some of the other services do not, and it's a real bummer when your machine is deployed and about 8 months later, the VPN provider says, we've rolled your credentials, please install this new credential on the machine, and you can't get through it. I have not yet met anybody that knew this, so maybe somebody will, but I'm trying to spread the word as much as I can. If you have a Starlink Mini and you read the fine print, for $5 a month, you can put it in standby mode. And standby mode comes with unlimited low-speed data for $5 a month. I have tested this. They have not cut it off. Unlimited low speed to them means roughly dial up. So 56K, maybe 100K on a good day. But that's plenty for a lot of what we do in the field. So you don't need the 50 or 100 or $150 plans. $5 a month, you can get your data back. Pretty incredible. The caveat to this is, for now, Starlink is a month-to-month contract. They can change things at any time. They just did a couple weeks ago, they put a speed limit on the Starlink Mini because people were throwing them in small aircraft, and now they've got in-flight Wi-Fi. Starlink said, if you have aircraft, you have more money. So they put a speed limit on it. Once you hit 80 miles an hour, the Starlink cuts out unless you pay $400 a month now. Okay, the last little bit here is things about working with instrument makers. There's always more to any project than meets the eye. I think everybody here would agree with that. The words quick and simple are the trigger words to know that you're looking at just the surface of a project, because you know that there's all of this underneath the surface, right? There's all these little concerns, and a lot of them we don't have answers to until you get to your field area. Like testing, this is one of the things that I think the whole Juneau ice field is a great area for. You don't have to travel that far to do some of this testing. That would be very difficult to do anywhere else. We can test a lot in the lab, but there are limits. Lead times on materials are becoming crazy right now. So there's all of these factors to think about, of course. And that's where working with somebody like what we do, we try to keep an eye on all this because we know you're busy doing amazing science. One of the key things is trying to know when it's going to cost you more for a DIY solution versus working with somebody else. This is a hard line to draw, and we do our best to try to say when you're crossing that line of you could really do this yourself and save a lot of money, or you should work with somebody like us because we do this every day, or we have the right tools and we can do it better, quicker, better. That's certainly not always the case, though. There's a lot to be said for DIYing it. The example this morning that you had of the GNSS station, that's way less than any of the commercially available products, is a great example of totally DIY that. Embedded software engineer friend of mine, Licia White, said this once, and it has resounded very true. That everything is a temperature sensor. Some things measure other stuff too. Really important to keep in mind when you're working with any instrument or instrument vendor. Yeah, this is some displacement sensor data, but it really applies to any instrument. It's just something we want you to know. If a manufacturer does tell you our instrument's not sensitive to temperature, they're either lying or they did some very elaborate correction that you probably want to know about because it may affect your data anyway. As geoscientists, we have the unfortunate situation of being in the space where our signals are generally diurnal, because that's the interesting process that we're looking at, but so is temperature. And sometimes our signals are driven by temperature. So there's this horrible convolution of things that we have to try to decouple. One of the things that I want to say is contact whoever you're buying instruments from early and often. Every stage of your project, there's nothing worse than for us than being contacted by someone who's had a proposal funded and they say, I put X dollars in the proposal to go do this, and having to tell them that's absolutely not possible. Or you budgeted way too much and now they have to do all kinds of gymnastics to move that money around to other parts of the project. So if you talk to us before you submit your proposal, we can help with that. We're happy to help with that. We do letters of collaboration and things all the time. Obviously, during the design build, we're going to talk to you a lot. During deployment, you're probably going to have questions. We're going to be talking to you there. This other side of the chart, though, really these two sides are kind of where we lose communication with you. After you deploy the instrument and it's working, we generally don't hear from you again. We'd really like to, because we want to know, what was your experience like? when you're going to buy more in the future or do more projects, how can we help revise that? And how can we share that information with the community? It is unreal how many problems have been solved multiple times because that feedback loop never completes between different groups that are doing research. And none of this is super secret. I don't know why some manufacturers want to try to keep everything. We're all just trying to make better stuff. So we like sharing it. And if you share your experience back with us, that helps. One other piece of advice, this is one of my favorite field pieces of advice. It can't fail if it doesn't exist. So don't overcomplicate your system. Don't make it do lots of things. Is anybody familiar with the phrase "yagni"? It comes from the software engineering world. As somebody from the South, I also love it. It stands for you ain't gonna need it. So if you're thinking about, well, I could add this feature and this feature and this feature to some, you're probably not going to use them. Implement it if you need it, but otherwise it's just more complexity. It's going to cause more failures in the field. And we're all working in this really complex, in-dimensional space where you're trying to trade off resolution of the sensor, which often you don't know what resolution thing. We say, what magnitude of signal are you looking at? And as geoscientists, we're lucky if we know the order of magnitude, right? So resolution cost is obviously a trade-off. Complexity, stability of the sensor is often a trade-off. How complicated is it to deploy? How much time do you have? How much power do you have? There's all these factors that go in to making this horrible landscape that you're trying to navigate, ideally to a global minima, but most of the time we're lucky if we land at a local minima, right? So that's where talking meetings like this with people that have done lots of different deployments and with manufacturers, we've seen lots of ways our sensors fail and other people's sensors fail. Again, being able to share that with you can help. Changing things about your field setup, really cheap to do in the beginning and really bad, roughly exponential later in the project. Again, I think we've all experienced this, but it's worth just reiterating. I think this is the last sort of tip, is telling whoever you're working with the whole story of a project really helps. That means, what your science goals are, because we're mostly geoscientists at our company. So if you tell us what the science goals are, we can help you pick better instrumentation instead of just coming and say, I don't use instruments. What your requirements are, the scope that you've got us, or this job in your proposal, the funding source. If you are trying to get funding and say, I need a budgetary quote, super happy to do that. That's a good thing to say up front. If you're saying, I need an absolutely binding quote because my university purchasing department needs to do this, that's also something that's really important to tell us. I don't know how many times we've done, especially seems to happen in laboratory control systems. We get a spec, we implement it, we get to the end, we hand it over, and they say, that works great. Now make it do X, Y, and Z too. And that was the plan all along, but because the whole story wasn't shared, it ended up costing a lot more money. So if you tell us the whole story, well, maybe next year when we go back, we're going to add a temperature string to the station, or we're going to add this to the station. We can go ahead and make those additions of oversizing the power system, of recommending more connectors, doing different things to make that system future-proof, but not overcomplicate it and save you some money. These topics and other things like them, we have a workshop called Gears that we run every August. Registration for this one's open, and it's for mostly graduate students, so we have undergraduates and professors come through as well. You spend a week at our facility building instruments. You get to get hands-on. You've never used a lathe or a mill. Well, you're going to that will give you a lot more appreciation for why that part you drew in CAD is going to cost $5,000 instead of $500. So you get to do that, and learn some soldering and field wiring, do some data collection. There's projects. We even go to some local industrial facilities, and you get to see how they protect their sensors in some really harsh, high pressure, high temperature environments. So it's a fun week. Encourage. I know several people that are on the call, or I don't think anybody in the room has been to this, but it's going to be year 6 this year. It's a lot of fun to do. With that, I'll take any questions if there's time. Otherwise, happy to talk offline. Be sure to check out. We have tutorial videos and stuff on YouTube. We have a podcast. There's all kinds of fun stuff there. So thanks.
Questions for John? We're gonna have a demo on Wednesday with some jumps.
Yes, I brought toys to play with.
Nice.
So we'll have that.
Point of opportunity.
Yeah, go ahead quickly.
I'll just get the next one going.
So in the tilt meters, at least the ones you were showing were small,
Right.
and I would normally think that, something like small would be mechanical advantage for measuring that tilt, but I'm just curious what the design benefits of the small footprint and what you might be trading off versus something like a cylinder and a borehole.
So we actually, even the borehole instruments use the same tilt elements, and they're about an inch long and a half an inch tall. At least they're the electrical technology. So we're not making really any trade-offs in the packaging. It's the same sensors. We have MEMS, which are lower cost, lower resolution, say 1,000s, 2,000s of a degree. We can get in very small packages, and then we go to the electrolytics, which will get you down into the micro radian or nano radian range. But packaging wise, it's really just what fits where we're trying to go.
Okay.
What are the installation procedures you have for your tilt meters to make sure you're getting kind of consistent readings when you're placing them at different sites?
Yeah, so that's tricky. Depends on what you're mounting to or what you're going into, of course. Bolting it down to rock with a rock anchor kit is the best. Otherwise, putting it on a large plate and burying it, even getting them this far down, is a huge advantage. Because you have the sun shining on it, get away from some of those really near surface effects. The key that we found is don't put them inside a large enclosed volume of air like box. That never works out too well. There was another instance of dark cases getting deployed on the surface and melting themselves into ice. Big gassed out. So yeah, really just trying to isolate thermal effects and trying to give them a big coupling footprint. Or if you're in a borehole, ideally grout them in. If you can't grout them in, we have some anchors that are swinging our anchors pretty well, but it's better to grout.
Thanks, John.